It's the second video for week 10. Here we are going to look at continuous functions. So let's define what we mean by a continuous function. Let's begin with a subset A of R and a function f from A to R and a point C in A. Then we say that f is continuous at this point C in A. We say that f is continuous at that point C if for any epsilon bigger than 0 that you pick, there will be a delta bigger than 0, okay, which depends on the epsilon that you have picked, such that if x in A satisfies a condition that the distance between x and C is less than that delta epsilon, right, then the distance between f of x and f of C is less than epsilon. So we say that f is continuous at a point C in A if for any given epsilon bigger than 0, you will find a delta that depends on epsilon, such that if the distance between x and C is less than delta, then the distance between f of x and f of C is less than epsilon. Now, if f fails to be continuous at C, then we say that f is discontinuous there. So we say that f is discontinuous at C if it fails to be continuous at C. Now let's look at this remark here. The first remark is if C in A is a cluster point of A, then saying that f is continuous at C is the same as saying that the limit as x goes to C of f of x is equal to f of C. You can see that from here. You can see that from here. Remember how we defined the limit of a function f at a point C? This one was L. Okay. Now instead of L, we have f of C. So if C in A is a cluster point of A, then f is continuous at C if and only if the limit as x goes to C of f of x is equal to f of C. All right. So this means that if C in A is a cluster point of A, then three conditions must be satisfied for f to be continuous at C. Now we are saying that f is continuous at C if and only if the limit as x goes to C of f of x is equal to f of C. So that means that this limit exists, and is f of C. So for this limit to be f of C, that means f of C must be defined, and that the limit must be equal to f of C. So if f is continuous at C, then the following three conditions must be satisfied. First of all, f must be defined at C, okay, so that f of C makes sense, okay, that the limit as x goes to C of f of x must exist, and that the limit must be equal to f of C. So three things must be satisfied. F of C must be defined, the limit as x goes to C of f of x must exist, and then the two must be equal, the limit and f of C. The limit as x goes to C of f of x must be equal to f of C. The second marker is the following. If C in A is not a cluster point of A, then there exists a neighborhood V delta C of C such that the intersection of A and this neighborhood contains only one point C. Hence, a function is automatically continuous at a point C in A, which is not a cluster point of A. Let me illustrate this by means of this picture here. Supposing this is your set A, okay? Okay. Supposing this is your set A, this one here, okay? And supposing this is your point C, right? Okay. Now, let me change a little bit. Supposing your set A contains this interval, let me call it the interval from alpha to beta, okay, union this point C. So your set A is going to be, okay, the interval from alpha, okay, up to beta, okay, union the point C, union the point C. So this is beta, this is beta. Then you see C is not a cluster point of A. Why? Because I can take a neighborhood here of C which contains no other point of A except C itself. I can take a neighborhood which contains no other point of A except C itself. Now, call this one, this is C plus delta, C minus delta, and then this point here will be C plus delta. So that will be C plus delta, okay? Right. Now you see, if you pick an element of X which lies in this neighborhood, an element of X which lies in this neighborhood here, that element, there's only one element which is C. So the difference between f of X, okay, and f of C, the distance between f of X and f of C, okay, the distance between f of X and f of C will be 0 provided X is in A intersected with this neighborhood. Because the intersection of A and this neighborhood is only a single point C. So if we say that X belongs to the intersection of this neighborhood and A, so that X must actually be C. So the distance between f of X and f of C will always be 0, so long as X lies between the intersection of this neighborhood and A. So that will be less than n epsilon, okay, bigger than 0. So that tells you that the function will be automatically continuous at a point C, which is not a cluster point of A. Now, we have the following two theorems. One is called the sequence criterion for continuity. The other one is called the discontinuity criterion, okay? The sequence criterion for continuity tells you that a function f, okay, is continuous at a point C in A if and only if for every sequence in xn in A which converges to C, okay, if you form the new sequence fxn, then that new sequence must converge to f of C, okay? So every sequence xn, a function is continuous at a point C if and only if every sequence xn in A which converges to C, okay, has the property that fxn, okay, will converge to f of C. That's what we call the sequential criterion for continuity. Now, if you can just get one sequence xn in A which converges to C, okay, if you can just get one sequence xn in A which converges to C, but f of xn does not converge to f of C, that will tell you that the function f is not continuous at C, and that's what we have down here. So it says a function f, if f is a function from A to R and C is a point in A, then f is discontinuous at C if and only if there exists a sequence xn. We just need one sequence. There could be more than one. If and only if there exists a sequence xn in A such that xn converges to C, but f of xn does not converge to f of C. Okay, so let's look at this definition here. you have A and you have a function f from A to R. We say that f is continuous on a subset of A if it's continuous at every point B. We say that f is continuous on a subset B of A, okay, if f is continuous at every point of B. Now, a function f may fail to be continuous at A because f of A is not, maybe a function f may fail to be continuous at C because f of C is not defined, okay? Because remember, a function is continuous, if C is a cluster point of A, then f is continuous at C if and only if the limit as x goes to C, f of x is equal to f of C. If C is a cluster point of A and C is inside A, then f is continuous at C if and only if the limit as x goes to C of f of x is equal to f of C. So a function may fail to be continuous at a point C because f of C does not exist because f is not defined at C. F of C is not defined. But if the limit as x goes to infinity, no, if the limit as x goes to C of f exists, then we can redefine the function f to make it continuous at C. Supposing now, supposing the limit as x goes to C of f of x is L, then you simply set f of C to be equal to L, and then you define a new function by setting, you define a new function by setting f of C to be that limit. You define a new function by setting f of C to be that limit. So let's consider this example here. We look at this function here. F of x is x squared minus 4 over x minus 2. This function is not defined at x is equal to 2, right? But the limit as x goes to 2 exists. You simply define, decompose this function as a, you note this one is a difference of 2 squares. You write it like that, okay? Then this x over 2 will cancel out with this x minus 2 will cancel out with this x minus 2. So you have this limit here, which is equal to 4. So you can redefine f to be the function that we have before if x is not equal to 2, and then you set it to be equal to 4 if x is equal to 2. Then the function will be continuous at 2 since the limit as x goes to 2 of f of x is equal to f of 2. So you have redefined this function to be continuous everywhere. As an example, we want to show that the function f defined by f of x is equal to x squared is continuous on R. So if C is any point in R, you just have to show that the limit as x goes to C of f of x is f of C. And now look at this limit. F of x is x squared, so we take the limit as x goes to C of x squared. That is just C squared, and that is f of C. So I've shown that for any C in R, the limit as x goes to C of f of x is equal to f of C, and therefore we conclude that f is continuous at every C in R, and therefore f is continuous on R. Excuse me. But at times you may be required to show that a function is continuous at a point using the definition, and that's what we do in the second part. So like we did before with the limit of a function at a point, we just need to write the distance between f of x and f of C in terms of the distance between x and C, and that's what we do here. This is the distance between f of x and f of C. Just simplify like this. Use a triangle inequality to get this. Then you need to bound this by some constant. So to do that, we assume that the distance between x and C is less than 1, like we did before. And then you use this inequality, okay? This inequality here to end up with the magnitude of x being bounded by 1 plus the magnitude of C. So you replace this one here by this one, right? And then you get this inequality here, okay? So you have that if you set delta equal to the minimum of these two, then if the distance between x and C is less than delta, then the distance between f of x and f of c is less than epsilon, so f is continuous.